Okay, now we're looking at implicit differentiation. Should be fairly simple for these problems. There's not too much that's tricky except for maybe one thing, and I'm going to point that out without pointing, but you can't see. I think, in my opinion, it's best to use the dy dx notation because if you're taking the derivative of something and this part doesn't agree, like this variable doesn't agree with whatever you're taking the derivative of, say you're taking the derivative dy dx, but you're taking the derivative of like y squared, then if these variables disagree, you do something, you take the derivative like normal, then tack on a dy dx. I mean, I say it down here in one of the steps, but that's why I think dy dx notation is useful. And if you're taking the derivative of a term involving only x, you just do it like normal. That's fine and dandy. If you have something that's x times y squared, I don't know why it'd be written like that. It'd be xy squared. You use the product rule here, so got to be careful with that because these are two different functions. And then you'd have to use the chain rule for that. That's the implicit differentiation part. So if taking, I've already explained this, if taking the derivative and the bottom doesn't agree with whatever variable you're taking the derivative of, then take the derivative like normal and tack on a dy dx. And move on. You group all the terms involving dy dx and then solve for dy dx. Usually you factor out stuff. One of the biggest mistakes that I see is some people get down to something like this. Dy dx plus 2, let's say 2y dy dx equals some other stuff. So they get to this and they factor it incorrectly. They say, okay, great, I'll factor out a dy dx. So they go dy dx times 2y equals all that stuff. When actually, this is wrong. You need to have something else. So it's actually 1, right? 1 dy dx plus 2y. So this should be 1 plus 2y. So definitely be careful of that. And that's what I mean by group all of these to one side, maybe get all your other terms to the other, and then factor out a dy dx properly, making sure you don't forget that 1, and solve for dy dx. So I would divide by 1 plus 2y on that side. So those are the general steps. Very, very simple. But there's another thing I'm going to point it out. If you're maybe evaluating, so like the question says up here, find dy dx when x equals something. You do all the steps, you solve for dy dx, everything's dandy. You're smiling because you're like, man, this is easy. I'm glad I'm gonna get these points on the AP exam. I'm gonna be a baller, and then I'm gonna get college credit, and everything's gonna be good because college is gonna be cheaper. Unless you're an engineer, you probably should take calculus again anyway, unless you get a 5. But you should be getting it. Okay, so if you need to evaluate dy dx at a given x value, they tell you x is something, and then you take the derivative, but your derivative maybe involves y. So like maybe you end up with something like this: dy dx equals 3x minus 2y over 2y plus 1. And you're given an x value, but you don't have a y value. And you start to panic, and you think, no, I'm never going to get a college credit, go get college credit, and my life's going to be terrible. And then that's, okay, I ran out. So you need a y value also. You go back to your original equation before you take any derivatives, plug in the x value that they give you, and solve for y. That way you can find a corresponding y value. I have kind of like an example for that. So you'd say, find the slope of the tangent line when x equals 4 for this function, or for that equation. Because I don't even know, for that relation. I don't know if it's a function or not. It's probably not, because it has x squared and y squared. It looks maybe like it's part of like a circle, like a hyperbola, or parabola. Not a parabola. Maybe a parabola. Who knows? I don't know. It's not a parabola. Okay, so for this is what I'm talking about. They give you the x equals 4 part. But eventually, maybe you take the derivative, and you find out that you need something like this. You have an x value, but you also need a y value. So maybe you find that out. Then what you do is you go back to your original equation before you took the derivative. I'm not saying that this is the derivative. I'm just not going to do that part. But you might end up something like this with an x and a y. So find the slope of the tangent line when x equals 4. Well, you found the derivative, but now you need a y value. You have an x value, but you need a y value. So you plug in x, and then you just have a quadratic, and you solve for y. In this case, you get two different y values. So then you would solve for y. I mean, I just did all the steps here. And if it said find the slope of the tangent line, there's actually two spots. There's two different slopes, which means it's definitely not a function because you get two y values for the same x value because it doesn't pass the vertical line test. But you'll get two different slopes. Maybe it's like an ellipse. Let's just pretend it was an ellipse. So we'd have something like that, and saying like, "Mel, find when x is 4." So maybe that's 4. And then you get two different slopes. So, well, I should write some stuff. You'd find the slope, here and the slope there. So you would get two different answers. You'd find dy dx, right? And then plug in 4, 9 because that's one of the y values, and also 4, 3. That's the other y value. So you'd find two different answers, two different slopes of the tangent line. Hopefully that makes sense, and I guess I got to stop this video, make another part. So I'll do that. Goodbye.